That's okay. So hello everyone. So welcome to quantum physics seminar. So today we have Professor Malcolm Kennett from Department of Physics, Simon Fraser University as our speaker. Malcolm did his master and bachelor in astrophysics from the University of Sydney. And after that, he moved to Princeton to do his PhD in condensed matter theory. So after graduation, he was a postdoc in Cambridge for a while. And after that, he joined SFU in 2005 as a faculty member. So Malcolm has a lot of research interests. He currently works on the oath of equilibrium dynamics in strongly interacting quantum systems with a focus on ultra-cold atoms. And also he studies the properties of quantum materials. So today he is going to tell us more about his recent findings. So let's welcome Malcolm.
Okay, thank you very much, Kiru. Today's talk is on out of equilibrium dynamics and information spreading in the Bose Hubbard model. And I'd like to thank support from NSERC and the Digital Research Alliance of Canada. Okay. And I'd also, to start with, I'd like to acknowledge the contributions of 3 excellent PhD students who have been involved in this work. Firstly, Matthew Fitzpatrick, who is now at UVic and shortly heading to Brazil. Ali Mokhtari Jazi, who graduated a couple of years ago and is now working for the Center for Excellence in HIV/AIDS, and Florian Baer, who is here but not here. And there's a variety of papers that we've been working on over a number of years, where all of the results that I'll be talking about today are contained in these papers. So to give you a little bit of a summary, I'm first going to introduce the Bose Hubbard model and then give you some motivation as to the work that we've been doing based on experimental observations of out of equilibrium dynamics in the Bose Hubbard model. So the particular examples we'll be looking at are correlation spreading in both 1 dimension and 2 dimension, and then slow dynamics. And I've put a question mark here because this has been speculated to be many body localization in the disordered Bose Hubbard model in 2 dimensions. Given that motivation, I'll then introduce the theoretical approach that we've developed in my group, the 2PI strong coupling approach, to describe out of equilibrium dynamics, and then show some results that we've obtained with that. And then I'll finish up with some discussion of how we've used machine learning to improve upon this 2PISC approach, and also mention some future directions as well. Okay, so let's people get in. Okay, so to start with, I'll introduce the Bose Hubbard model. This is basically the simplest model you can have for interacting bosons on a lattice. The Hamiltonian is up here. We have a hopping term, which is where all the kinetic energy is. The strength of that hopping is governed by the parameter J. We have a chemical potential, mu, which controls the filling of the lattice. And we have an interaction strength, U, and that interaction only takes place on site. So this is sort of the simplest version of the model that you can have. And so you can see that as we vary the ratio of popping, which is kinetic energy, to interactions, this is going to vary or change how the bosons behave. So in the limit of very weak interactions, so U is much smaller than J, or J over U is very large, then we get a superfluid phase. When J equals 0, we get a mod insulator. And then at some finite value of J over U, we get a transition from one phase to the other. And what I've got plotted here is the mean field phase diagram. This is relatively straightforward to calculate, and the insulating phases here, you'll notice, are denoted by these are called Mott lobes, and we have the n equals 1, n equals 2, n equals 3 Mott lobe, and n here tells us how many bosons we have per site. So n equals 1 is an insulator with 1 boson per site, n equals 2 is an insulator with 2 bosons per site, and so on and so on. Okay. Any question? By the way, if you have any questions at any point, please just jump in. I'd like everything to be as clear as it can be. Okay, so just to sort of give you some more interest on why we might be interested in the Bose Hubbard model, sort of in analogy with the fermionic Hubbard model, which is used for studying high TC superconductors and other strongly correlated quantum materials. The Bose Hubbard model is the simplest model of interacting bosons on a lattice. It can describe Josephson junction physics in certain limits. It can also be realized experimentally in cold atoms, and that's where we're mainly going to be talking about it today. There's also been proposals for its use for or realization for photons in cavities, polaritons, and even as a toy model for emergent spacetime. So it's a model that has quite a lot of interest from quite a lot of different directions, and so understanding its properties is, I think, a worthy endeavor. So the physical system where it can be sort of studied with the most control is cold atoms and optical lattices, and how this works is that atoms have some polarizability. So if you put a polarizable atom in an electric field, that will induce a dipole moment. And then the potential energy of a dipole moment in a field is given by minus d dot E. So if you create a periodic electric field through standing waves of lasers, then you will be able to create a lattice, and the atoms will sit where their potential energy is minimized in that lattice. So by this is done by creating standing waves of laser beams to have a lattice that atoms sit in. In addition to this lattice, there's actually also a harmonic trap, which sort of confines the atoms and stops them just flying away. That can actually be quite weak, so we can have something that really looks pretty much uniform if we're looking at a small enough system. And the reason that this is very attractive is that these optical lattices are very versatile, so you can control the strength of the lattice, so the depth, you control dimensionality, or even the type of lattice you have by using lasers. So you could have a square lattice, rectangular lattice, triangular lattice. The limit is really your imagination and your laser budget. My background is in condensed matter physics, and so this is what got me interested, because basically what we have is quantum particles in a periodic potential, and as a theorist, that's a lot about how I think about materials. However, there are some differences. So there's no disorder here unless you want there to be. You have the flexibility to tune parameters. It's not like you have a lump of quantum matter on your desk and you can change. Well, you can change the lattice if you apply enough pressure, but it's not the easiest thing to do. And because we're now looking at bosons rather than fermions, we can perhaps get to quantum phenomena that aren't accessible in materials. So the idea here and sort of the connection to sort of the quantum side is that there's a potential here for use for quantum simulation. There's also been suggestions for using cold atoms in optical lattices for quantum computing as well. I won't really be touching on that side of things. I'll be really mainly talking about the Bose Hubbard model.
So by no disorder, you mean the quantum simulator, the trapped atom has no disorder? Is it a good thing or a bad thing?
Well, I'd say it's a thing.
It's a thing.
So I mean, if I create a standing wave, from the lasers, that has no disorder in it. Whereas if
even the potential has no disorder, or the atoms are not sitting in the sites.
Well, the atoms, I mean, the atoms are sitting at sites in this lattice. So, I mean, you can have disorder in the sense that not every site is occupied.
Yeah.
But there's nothing that distinguishes one site from another that says, okay, it's energetically unfavorable to sit on this site as opposed to the other sites. I mean, you can make and I'll talk a little bit about this later on. You can make a speckle pattern that you pass your laser light through. That means that you do in fact have different potentials on different sites, and so there is something that mimics the disorder that you get in a material, but you don't necessarily have to have disorder, and so that's nice in the sense that it allows you to sort of understand the clean problem, and then you can add disorder and see how disorder changes things as well. Any other questions while we're there? Okay, so I already mentioned the phase diagram a little bit, but just to sort of clarify a little bit more, in the weak interaction limit, the bosons can basically roam around on the lattice and form a phase coherent ground state, which is superfluid. On the other hand, if I turn off the hopping, then the Hamiltonian becomes very simple. It becomes basically a single, n copies of a single site Hamiltonian. So if you solve this single site Hamiltonian, then you know what the phases look like. So if I have R bosons on the site, then I can find that the chemical, well, I can alternatively find the chemical potential that minimizes the energy for a certain number of bosons on the site. And if mu over u is between r minus 1 and r, then the energy is minimized for r bosons on each site. And then I'll get degeneracies when mu over u is equal to an integer. So we'll just hop back up. That's these points on at the intersection of these Mott lobes. Okay. And the states here are localized. There's no phase coherence between the different sites because this is basically a single site problem. And we get an insulating state. And then, as I mentioned, as we turn on hopping, we can go from this insulating state to the superfluid state there. Okay, so one more comment about sort of the experimental setting here. I mentioned earlier we have a harmonic trap. So what that means is that we can think about there being a local chemical potential, which is global chemical potential minus the harmonic potential. And so as I go to different places in my system, in my trap, the local chemical potential will vary. So as the, if I start, say, with some value of mu at the center of my trap, which is, say, sitting here, and then as I increase the radius, the chemical potential will get smaller, and I'll cut through various parts of this phase. So if I start with small hopping, I can say start in an n equals 3 mod insulator and have rings of n equal 2 and n equal 1 mod insulator. On the other hand, if I start with a large value of the hopping, I start with a sort of more dense superfluid and go to a less dense superfluid. And this is sort of known as the wedding cake structure for obvious reasons. One of the things that you'll find in a lot of experiments that are done these days is that the system or the harmonic trap is chosen to be shallow enough, or the system is chosen to be small enough that we just sit, say, in one of these Mott lobes rather than having all of the various Mott lobes. So just to it gives you some experimental observations of what this actually looks like rather than a theorist's eye view. Here's some imaging of from the Chin group at University of Chicago showing a wedding cake, and here's some imaging, I think, from Greiner's group, also showing 4 different Mott insulator shells. So here's the inner one, and then various additional shells. Okay, so that sort of hopefully gives you a bit of a background to the Bose Hubbard model and its realization in cold atoms. Now I want to sort of get onto the experiments that motivated the work that I'll be talking about today. So these parameters J and U depend on the lattice depth. So the hopping depends exponentially on the lattice depth, while the interactions basically go like lattice depth to the power 3/4, I think. And so if you change the depth of your lattice, then you change the ratio J over U, so you can go from the superfluid to the Mott insulator or vice versa. One particular type of quench that's been explored quite a bit is to start with J basically 0 and then increase but stay in the Mott insulator. So if that would be sort of starting here, quenching to say a point here, but just so making this change in parameters and then looking at what happens to the correlations of the particles as a function of time. So here's sort of the first experiment that did this in 1 dimension. And what you can see here is the particle-particle correlation as a function of time at a distance of 1 lattice site, 2 lattice sites, 3 lattice sites, 4 lattice sites, and so on. So you can see that the strength of the correlation decays with distance, and that the correlation spreads through the lattice. Here is distance versus time, so taking this and digitizing it here. You can see that there is a roughly linear spreading of these correlations in time. So you have ballistic excitations. Yeah, that would be great. Thank you. Okay, so back in 1972, Lieb and Robinson actually showed that there is a maximum speed at which information can spread in a non-relativistic quantum system. there's a couple of caveats to this result that mean that this doesn't strictly apply to the Bose Hubbard model. One of the caveats is that you have to have a bounded local Hilbert space. That's not the case in the Bose Hubbard model. So it's not required that there be a bound on the speed of information spreading, but it is possible to show in for certain special initial states that there is a bound on how fast information can propagate. And as we'll see, as you saw in the experiment before, and as we'll see, for a number of cases, there does seem to be a bound to how fast excitations travel, even if this is not something that one can prove. So in the example that was considered experimentally, here there was some work by Barmettler et al. To calculate what the maximum velocity would be in this case, and they found this formula here. So D is the lattice spacing, and then we have J over U, and the velocity goes like 6JD over H bar in one dimension. Beyond one dimension, there are no exact numerical or analytical methods to calculate spreading of correlations in the Bose Hubbard model. Sort of the simplest example of an estimate in higher dimensions is given by Kratitsky et al., which is basically square root of D times the result from one dimension. And so the sort of theoretical challenge that motivated us was, can we come up with come up with a more quantitative estimate of the speed at which correlations spread in dimensions higher than one, because many of these numerical approaches are mainly limited to one dimension. This suggested that we use an analytical approach. So this is sort of the motivation. And then after we'd done some work on this, there was an experiment that looked at the spreading of single particle correlations in 2 dimensions. So this was by Takasu et al. In Japan. And here they look at basically, so here's time 0, and then increasing time, and you can see these correlations spreading outwards. Here again, you can see peaks in this case, the single particle density matrix, and then here's a plot of where the peak is as with distance versus time, and you can see that this is roughly linear. They're only able to look at relatively small system sizes, but they were able to extract a velocity. Here they found a peak. So the peak here, they found had a velocity of about 13.7 JD over H bar, and then the dip, some plots here have a more pronounced dip than others. They found the trough goes at about 10.2 JD over H bar. So if we go to the D equals 2 estimate from Kratitsky, we get 8.4 JD over H bar, which is clearly quite a bit less than these numbers. And we'd also done a more thorough calculation, and we got about 8.1 JD over H bar, which is also, which is of similar magnitude, but definitely quite a bit less than that. So how do we reconcile this discrepancy? Well, this basically comes back to first year physics, which is, when we have signals propagating, we have to worry about both phase and group velocity. And so Takasu et al. Suggested that what they were measuring is actually the phase velocity rather than the group velocity. And this is corroborated by calculations of single particle correlations in one dimension using matrix product states by Desprez et al. Here you can see it's not the easiest to see, but you can, they plot both peak positions and center and wave packet positions to extract a group velocity and a phase velocity, and they find that as a function of u over j, as you go to larger values of u, the phase velocity becomes a lot larger than the group velocity. So this is a d equals 1 result. We will see whether this also holds in d equals 2. Okay, so that's the first experiment that motivated our work. The second comes from looking at the disordered Bose Hubbard model. So this is basically what we had before, but now we've added one more term to the Hamiltonian. We have a random on-site potential epsilon I, and so we have otherwise the same physics. And what this does to the phase diagram is that at large values of hopping, we still have a superfluid. At 0 hopping, we can have a mod insulator, but we could also have a Bose glass phase. So this is a phase where we our particles are not localized in the same way as they are in the mod insulator. There can still be some local phase coherence, but there's no global phase coherence. And experimentally, this was realized in a 2-dimensional optical lattice by Choi et al. They have a potential that they apply to make a random potential in their optical lattice. And what they did is that they started off with half of the atoms on one side of the lattice and looked at how the atoms spread as a function of the disorder strength. So delta is basically the width of the disorder potential distribution. And when you start with no disorder, you can see that the atoms spread out to cover the lattice uniformly. But if you start from larger values of disorder, then the atoms are, it's not as easy to see, perhaps as you'd like, but you can see that more of the atoms seem to be hanging out on one side of the lattice than the other, and that's on the side that they started on. So so they speculated that this is, well, clearly this is not thermalizing because atoms aren't spreading out everywhere, and they suggested that this might be an example of many-body localization. So just as an aside, what is many-body localization? So if you have a many-body localized system, then all of the many-body eigenstates of the Hamiltonian are localized. So if I take an isolated quantum system, what we usually expect is that thermalization will take place. This is the basis of statistical mechanics. And in that case, we expect that the system can be described by the microcanonical ensemble. And this is known as the eigenstate thermalization hypothesis. So many-body localized systems violate the ETH. So, okay, does this actually happen? Well, in one dimension, there's quite a bit of numerical evidence and some rigorous theory that under certain circumstances, it is possible to get many body localization in one dimension. For dimensions higher than one, at least theoretically, there's quite a number of arguments that we should not be able to have many body localization in dimensions greater than one. And the reason for this is that sort of we get rare thermal inclusions in our 2D system, and they can act as a bath that thermalizes the rest of the system. And this is quite complicated theory, and I'm just presenting a cartoon, but this is sort of, this is a question that has been around for a number of years. So this experiment suggested that maybe we can get an answer to this problem by using the Bose Hubbard model as a quantum simulation of the 2D interacting disordered quantum particles. So the experimentalists looked at the imbalance, so the number of particles on the left-hand side of the lattice minus the number of particles on the right, divided by the total number of particles as a function of time and disorder strength. So here we have the imbalance as a function of time with increasing disorder strength, and you can see that when the disorder gets strong enough, it seems to be saturating. And if you plot this long time value here as a function of disorder strength, you can see that there is it seems to be a transition from basically zero imbalance to non-zero imbalance at different values of as a certain value of delta over J, and these are two different values of U in this experiment here. So, okay, that's sort of the introductory part of my talk, why we're working on these problems. And so the challenge theoretically is that what we need to do is we need to calculate out of equilibrium dynamics of disordered interacting bosons on a lattice. We'd also like to be able to include a trapping potential if we can. As I mentioned, beyond one dimension, exact methods aren't available. So this is going to have to be an approximate method. And given that numerical approaches are mainly limited to one dimension, we approach this analytically. So what do we do? The next few slides are going to be quite technical. If you're not interested in the technical details, you can take a quick nap, and I'll wake you up when we start talking about results from the formalism. But for those of you who are interested, we use a two-particle reducible approach within a contour formalism. So what we want to calculate are the superfluid order parameter and the two-point Green's function. As this is an interacting out of equilibrium quantum problem, we use the closed time path or Schwinger-Keldysh technique. The advantages of this is it allows us to calculate both at zero and finite temperature in the same formalism, and it also allows us to do disorder averaging as well. So we can look at disordered systems as well as clean systems. The 2PI part of the approach basically corresponds to the diagrams that we keep when we're constructing our field theory. And the nice part about doing this is it treats the propagator and the order parameter on equal footing. And again, it allows us to describe both equilibrium and non-equilibrium behavior. So what we do is we put our theory on a Schwinger-Keldysh contour. So we promote the theory from living in real time to being in complex time. And this is a contour in complex time. It starts at time equals minus infinity, goes to time equals plus infinity, and then comes back again. What this does is it doubles the number of fields in our theory. And so we have a second copy of the field that propagates backwards in time. You might be worried about this. This is really just an accounting mechanism that will allow us to construct our field theory. And then once we've done that, we forget about the contour and don't worry about it. So, okay, so what we are doing is calculating equations of motion for the propagator and the order parameter. There's, in terms of how we do this, we start with the Bose Hubbard model and we take a couple of Hubbard-Stratonovich transformations. The reason for this is it puts the, and if you want more details about this, just ask me afterwards. But it allows us to put our theory in a form that lets us describe both the superfluid and the mod insulating phases. We truncate our action, and in very condensed notation, we basically have a quadratic piece and a quartic piece. The quadratic piece has hopping. We have a piece that comes from local interactions, and then we have an extra piece, this U tilde, which I'll mention in a moment, and then we have interactions, which give us this U term here. So the G2 here is the atomic, so J equals 0, two-particle Green's function. These curly G's are one-particle Green's functions. And this U generates physical diagrams, and this U tilde, well, it generates diagrams that are both physical and anomalous. And this U tilde allows us to cancel out the anomalous terms. If you kept terms to infinite order in this action, you wouldn't have to worry about cancellation of anomalous terms, but when you truncate a particular order like we have, you have to make sure that you cancel out these terms. So it's also possible to calculate a disorder average. There's additional Hubbard-Stratonovich fields that you have to include in this case, and we end up with an effective theory, which again has a quartic piece, and now it's possible to have, well, we have quartic pieces as well, and I've represented the field here. The Z term is what we had in the Kling case. This Q field enters because of the disorder averaging. So if we drop the Q term, then we're back to the Kling case. But I'll use this notation because it allows us to refer to both. So we have an effective theory that looks like that. And from that, we can define our mean field, which is the expectation of this field phi, and the full propagator, which is correlations of this phi, and get the equations of motion for the mean field propagator. In terms of diagrammatics, for the 2pi theory, these are the two-particle, this is, well, the two-particle contribution to the effective action, this gamma 2 term. We only keep diagram A here, known as the double bubble. This is basically a Hartree-Fock-Bogoliubov approximation. And from there, we get equations of motion that we can go ahead and solve. So for those of you who were taking a little bit of a nap, now you can wake up, and I'll show you some results that we get from this theory. So first thing that we did is to say, okay, let's try and get some equilibrium results when there's no disorder, see how we do. So the blue line here is the mean field result. The red symbols, these, depending on dimensionality, are DMRG or quantum Monte Carlo. So in equilibrium, you can use numerical methods for the Bose Hubbard model in dimensions higher than 1, and you can calculate the phase diagram. And then in black, what we have is our effective theory result. And so you can see that we do a lot better than mean field theory. In 3 and 2 dimensions, we get, we don't perfectly match quantum Monte Carlo, but we're very much ahead. And in 1 dimension, one of the features that we capture is this cusp in the phase boundary. We don't capture it in exactly the right place, but we do capture it, and mean field theory has absolutely no signature of it at all. So we're definitely doing better than mean field theory, which, given the amount of effort we put in, you'd really hope that we did. Okay, we can also look at what happens when we add disorder potential. So here, the blue line on the outside, or blue symbols, this corresponds to the 0 disorder limit. And then as you increase the disorder strength, you can see the Mott lobe shrinks in size. And this happens in 1, 2, and 3 dimensions. If we compare our results for the phase boundary to quantum Monte Carlo, we're able to get the mod insulator Bose glass transition, and it's not perfect, but it's about as good as we had in the clean case. And then one thing that we looked at was let's look at the parameters where this potential many body localization transition was taking place in experiments. So if you, that would be this red dot here. Here's the phase boundary calculated by our method, sort of taking into account some couple of different values of delta over J here, basically corresponding to different error bars. And if you use the quantum Monte Carlo values for the transition, you find that they actually lie exactly on top of this your suggested transition. So this seems to be at least evidence that perhaps what's being seen in experiment is not a many body localization transition, but actually a mod insulator to Bose glass transition, which is still very interesting, but perhaps not quite as exciting as many body localization in 2 dimensions, which there are lots of reasons to believe shouldn't happen. Okay, so that's some equilibrium results. If we go to out of equilibrium, we're going to focus primarily on quenches in the mod insulator regime. Being in the mod insulator regime, that means the superfluid order parameter is 0, and then some of these anomalous correlations are also 0. What we do is calculate the single particle density matrix, which we can relate to one of the propagators that we calculate with our theory. We've done some benchmarking to compare with exact diagonalization in 1 dimension, and we'll look at the spreading of correlations after a quench. So here's some comparison to exact diagonalization for an 8-site chain. And we have results for delta R equals 0. These are not as great as we'd like. in exact diagonalization, you have particle conservation. Our theory doesn't actually conserve particles. It's a problem that you have with doing these types of out of equilibrium calculations. But yeah, we have agreement at about the 5 to 10% level in terms of the number of particles per site. If we go to delta R equals 1, 2, 3, 4, you can see that we capture the phase of the single particle density matrix pretty well out to, at least for the first set of oscillations and maybe even more, depending on delta R. And the amplitude, is not bad as well, at least at this particular value of parameters that we used. Okay, so this gave us confidence that despite we've made a variety of truncations to our theory, but we threw out certain diagrams, we cut it off at quartic order, but we're still getting pretty good agreement with exact physics, even despite these approximations. So we went ahead and looked at the spreading of correlations in one dimension. Here we're taking the hopping as a function of time. It has an abrupt jump, and then we're looking at how does the single particle density matrix evolve. We fit the envelope of this single particle density matrix and use that to extract the center of the wave packet, and you can plot that the position as a function of time, and there's exact results for the peak at a given R or delta R that were obtained in the strong coupling limit by Mettler et al., which are the orange dots here, and you can see that numerical results agree pretty nicely with those exact expressions. So we can also go ahead and look at the spreading of correlations in 2 dimensions. You see them spreading out at various snapshots. You'll notice that there's appears to be a certain level of anisotropy. This is not a perfect circle spreading out. It seems to be a sort of squared circle, and we'll come back to that in a moment too. And then we can also look at the phase and group velocity. So if we look at the position of the peak of the single particle density matrix, we extract the phase velocity, and if we look at the center of the envelope, then that gives us, of the wave packet, that gives us the group velocity. And we can see here, this is for a given value of u. We see a clear difference between the peak velocity and, the phase velocity and the group velocity. And then we can plot this for a variety of values of u over j. And if you cast your mind back to earlier in the talk, we see a at least qualitative agreement with Desprez et al. That here goes the phase velocity, is the group velocity. And then if we zoom in this little corner down here, we can compare to experimental measurements of the velocity from Chenot et al. We get a nice agreement with these red points, and then Takasu, they took data in 1D, and we seem to be roughly in agreement with that as well. If we go to 2 dimensions, again, we can calculate the phase and group velocities. And here we differentiate between the spreading along the crystal axes and along the diagonal. We see that these 2 are different. But we also see that our results compatible with Takasu et al.'s experimental results. These are the only experimental results. So, obviously we'd like to be able to make comparisons out here, but we're not able to. But, certainly everything seems to agree. And here is a comparison of the spreading of correlations that we find numerically with the experiment on similar size systems. So again, so we're pretty happy that we're able to get this this agreement. Okay, but there are places where we don't agree so well. So our effective theory does a great job of calculating velocities accurately, which is basically the phase of the single particle density matrix. But if we look at the amplitude, then as the strength of the hopping increases, our theory becomes increasingly inaccurate in getting the amplitude right. Here's the amplitude from exact diagonalization. Here's the amplitude from our effective theory. So Ali thought, well, maybe we can use a neural network to sort of correct our data so that it's correct our effective theory so that it produces the right value of the amplitude at a given value of J over U. So what we did is we took a bunch of single particle density matrix traces for system sizes up to L equals 11 and a variety of values at J over U. And this is a region where we can do exact diagonalization. So we got the exact diagonalization results. We fed in the effective theory and trained our neural network to figure out what adjustments it needs to make to this result to get here. And it's not just adjusting the amplitude, it's actually trying to adjust both the amplitude and phase. And I'll show some results here. So in one dimension, we can actually do exact diagonalization to slightly larger than L equals 11. So outside the training region, L equals 14 and L equals 13. Here's in blue is our effective theory, and then you can see that the neural network results lie very close to the exact diagonalization results, even outside the training region, which we're pretty happy with. And it seems that the key ingredients for having this scheme work are that you need a reasonably accurate approximate theory. If you sort of input just a flat input, this doesn't work very well. You need to be able to find exact results in some part of parameter space, and then our approach basically treats this as an image reconstruction problem. So you're feeding in the blue image to match the green image. Our neural network can output the red image, basically. That's the way to think about this. And we actually tested sort of extrapolating beyond the training regime a little bit more. So we trained on a restricted data set with only up to L equals 7, and then did a comparison with L equals 14 data. So you can see, so now we're looking at a system that is twice the size of what we trained on. And it's not quite as good as when we trained up to L equals 11, but it's still a massive improvement on our inputs. So, we hope that this might be useful for your strongly interacting quantum systems where you're restricted in what you can calculate exactly, but you have some decent approximate theory. I also just want to show you some 2D results. Here we're more limited in the sizes that we could look at, but again, we do much better than improve on the effective theory as we increase the strength of J and get very nice agreements. And we also did tests sort of extrapolating outside the training data and got similar results to D equals 1. And I think my time's basically up. So I'll finish there. And I'll just add a quick comment about some future directions that we're working on. So one thing that we're working on at the moment is extending some of these ideas to multi-component Bose Hubbard models, and that's what Florian has been working on. There's a paper here with some of our results there. And we're also starting to think about looking at extended Bose Hubbard models where you have interactions that are not just not just on site, but between different sites as well. And these both have their applications to various cold atom systems. So thank you for your attention.